Hi, I'm Pramod Mathai. I'm a postdoc here at the Center for Nanoscale Science and Technology inside NIST, Gaithersburg. I have a joint appointment with the University of Maryland in College Park, and I'm going to talk about a technique that we recently developed for both translating and rotating nano-objects in solution. A 10 micron long rod, shown in red, being translated and rotated along a square path shown in black, and the numbers that you see flickering around the periphery, the 8 numbers that you see around in the gray oval boxes, are the voltages being applied at the electrodes. The electrodes are placed at the boundary of the device, and the resultant electric field generated by these voltages forces the fluid to follow the electric field pattern. So the blue arrows shown in the movie are the directions of the electric field and the resultant flow field pattern. And what they do is both translate and rotate the rod due to viscous drag. The voltages are adjusted so that the fluid around the rod both pushes as well as shears in accordance with the desired translational and rotational velocity that we input for the control path. This is an example device where you have a layer of PDMS that has microchannels cut through it at one interface and reservoirs leading up to the microchannels. And this entire microfluidic device is placed on a glass cover slip, and what we do after this is inject the fluid along with the nanoparticles through these reservoirs, and the fluid finds its way from the reservoirs all through along the microchannels to the center of the device. A number of advantages with this technique. The first one being the rod doesn't have to have any special properties. All we do is rely on viscous drag. That's a property inherent between any fluid-solid interface. So as long as the rod is submerged in the fluid, we should be able to rely on the viscous drag to both translate and rotate the rod. So the rod doesn't have to be magnetic or birefringent or have any other special properties. Another advantage is that our technique can in principle be tailored to suit the particle shape. So there's a couple of gain parameters that we use in our feedback loop. These can be adjusted to make the rod translate and rotate when, for example, the rod is helical. The final advantage is that this device is really simple to make. One of them would be nanofabrication, where you could use this technique to both translate and rotate carbon nanowires and just metallic nanowires to build optical circuits, for example. Another application would be in force microscopy, where you could use this technique to probe the underlying fields at, say, a metal dielectric interface that lies below the particle. Third application would be in biology, where you could, for example, use this technique to control a sensor and point it at a cell that is floating around in its natural fluidic environment.